Let me start by thanking the organizers for inviting me to speak at this wonderful conference to share our results and learn about very interesting and inspiring things. So today I will tell you about some old and as well as recent work about how we use string field theory to learn about CFTs. So traditionally, people use CFT as a tool to learn about string theory, so I will try to go in the opposite way. So this is the brief outline of this talk, roughly divided in 3 thirds. So in the first part, I will tell you about how classical solutions in open string field theory correspond to consistent boundary conformal field theories, and how can we learn, what can we learn about possibly new boundary conformal field theories. And the second third of this talk, I will use an ancient technique by Ashok Sen and Mukherjee to construct some exact all-order perturbative solutions for nearly marginal deformations in open string field theory, and tell you what can we learn from this. And in the last third, I will look at this in the context of closed string field theory, to learn not about consistent boundary conditions, but consistent bulk backgrounds. So this is a very brief review of string field theory, especially for the young audience. So it's a very ancient subject that this action of Witten was written down in 1986. And essentially the degrees of freedom are contained in this string field, which lives in the open string Hilbert space. There is this first quantized BRST charge that acts on it as sort of an exterior differential form. There is this associative star product, and this bracket is like a Witten trace or integral. And this action has a beautiful property of gauge invariance and many beautiful properties. So early on, people used, like already in 1990, Kosteletsky, Samuel, and others used this action to address the fate of the open string tachyon. Okay, they were using a vertex that was worked out by David Gross sitting here and Javitsky. But they didn't learn much. Okay, they found that the tachyon can indeed condense, but they didn't learn anything about the endpoint of the condensation. But things changed after 1995 when Joe Polchinski from here, from Santa Barbara, discovered D-branes. And soon after, Ashok interpreted, using this insight, interpreted the open string field theory action as the action for the collective degrees of freedom on a D-brane, and made a series of remarkable conjectures. So in modern terms, the sense conjectures can be summarized simply by saying that classical solutions of open string field theory correspond to consistent boundary conformal field theories, period. And for example, if you want to learn about some properties of these boundary conformal theories, so there is a detailed correspondence that has been worked out since then. And like the simplest condition is that the action of the Witten's action evaluated on the solution is given by the change of the G function of the BCFT. Okay, so remember that to formulate the action, we need some initial boundary conformal field theory, which has its own G function. And the new solution, the solution that we construct, if it's different from 0, corresponds to a different solution with different G, and this delta G is measured by this action. And there's this factor 2 pi squared was famously calculated by Ashok. Okay, so I don't need to review what the G function is, because it was beautifully reviewed by Tadashi yesterday. But it just suffices to say that if we consider cylinder amplitude on a long cylinder with length t, and at the endpoints of the cylinder we put some boundary conditions, alpha and beta, described by some boundary state, and we take logarithm of that for large T, then that asymptotically it behaves as some universal, some P's dependent on the ground state of the bulk CFT, and then there are two finite pieces that don't vanish in the T going to infinity, and they are given by so-called boundary degeneracy, so boundary entropy. And the thing, the inside the logarithm, this is the 1 point, the disk partition function, and that's called boundary degeneracy. And these numbers has been computed by Cardy and many other people, and they are known in rational boundary, rational conformal field theories. So about the sense conjectures, back to sense conjectures. So there is a very simple class of classical solutions of open string field theory, which excite the universal zero momentum tachyon and some descendants of it, and BC ghost descendants. And this state corresponds to a state where D-brane completely decays to nothing, and therefore it has a zero boundary state, therefore it has a zero G function. And this conjecture has been checked in 1999 numerically by Ashok and Barton and Watty Taylor, who's been giving talk on F-theory compactifications today, and I contributed to it in 2005. Today, we have the most general proof of sense conjectures in one direction. That was given by, in two papers by Ted Adler and Carlo McCaffery, who managed to construct classical solutions in string field theory if you are provided arbitrary BCFT, of course with the same bulk as yeah. Okay, so I'm not going into to describe the construction, but I'd like to emphasize that this proves sense conjectures in one direction. It shows you that BCFTs can be seen as classical solutions of open string field theory, but it doesn't tell you that all open string field theory solutions are describing BCFTs. This is something that people believe, but has not been proved. Yes?
If the D-brane disappears, how is energy conserved?
Well, it's like if you are looking at a minima of potential, right? So you can have you can have one potential, you can have two different minima, the energy is different, right? So you're looking like for, yeah, so typically when you consider like a dynamical process, the energy is conserved, and then it's interpreted by some rolling tachyon solutions, is interpreted as going into the bulk closed string states. Yeah, so to show sense conjectures in full generality, we would need to prove that for any given, for arbitrary classical solutions, we would have to extract formally the 3-point structure constants of the vertex operators of the new theory. We would have to, of course, identify what the operators are using the shifted cohomology of the theory, and then show that these structure constants obey the Cardy-Levelland conditions and some other conditions, and this is so far probably unfeasible in a short near future. But some results have been obtained by the use of topological defects with some classifying algebra relations that people using CFTs as consistent conditions. So we were able to see them from simple considerations of classical solutions to OSFT. So, but we can still believe, or we can use it as a useful hypothesis that classical solutions of open string field theory correspond to something in boundary string field theory, and we can actually construct the boundary states. We can construct the structure constants, and then we can test, if we find something new, we can test whether it obeys all the consistency conditions. So this is the ideology that I'd like to use.
Question? So in order to prove the converse statement, don't you also need to know the BCFT condition for a time-dependent background?
For time-dependent?
For general time-dependent background, since you would be considered time-dependent solutions, right? And that's quite subtle. It's not obvious what the conditions are.
Okay, I haven't been thinking much about.
Yeah, but you have OP axioms of,
it would be a non-uniform CFT and it would be rational.
yeah, but I'm not sure if the consistent conditions is even fully understood. That's a trade.
I think the cardinal condition still makes sense.
I'm not sure even whether the notion of OP convergence may make the conventional sense.
Okay, I haven't been thinking much about these time-dependent boundary conditions. Yeah, but I'm sympathetic to what Matthias is saying. Okay, so so if you really want to find something new and learn about some new BCFTs, we have today we have essentially two possibilities, two possible approaches. You can either crank it up numerically, which actually surprisingly is something that works better than some other numerical methods that people use in CFTs, like the truncated conformal space approach, or we could use perturbative solutions. So this will be the second third of this talk. So let me first review some numerical things. So the ideas go back to 2000 when Nick Mellor, Ashok, and Barton constructed some low-dimensional D-branes as tachyon lumps. So they were essentially considering like D25 brane and found some lump-like solution that they interpreted as D24 brane. Then later we generalized this or adopted this philosophy to study something new. So we tested it in the context of the simplest rational CFT, which is the Ising model, and we are actually able to get the three boundary conditions that are possible in Ising model. So from string field theory, and what you also discovered that it's possible to go also like to construct solutions of higher G function. So solutions which are not necessarily constructed by tachyon condensation by relevant flows. So in some sense, they correspond to irrelevant flows, but string field theory still knows about them. And then Matěj Kudrna has done nice work where he analyzed the Wessumino-Witter models and group at perimeter studied this for conformal defects, and there are some very nice results there. So the general idea, if you want to study some concrete boundary conformal theory, has been already outlined in the first day talks by Scott Collier and Victor Rodriguez. Essentially, we take the BCFT of interest with some central charge C. We complement it with some auxiliary BCFT of central charge 26 minus C, and then we put the BC goes with minus 26, and then we have consistent open string field theory. So let me illustrate it with something that you might not be aware about. So this is some work in progress with Matěj Kudrna and Jakub Vušmera. So actually, Ashok-sen has already reported about our results something like 5 years ago at some strings conference. So we are a bit embarrassed that it's taking so much time, but it's not that there will be some fundamental technical difficulties, but now we are like nearing completion. So consider CFT, which is described by like a toroidal compactification on a equilateral two torus with 120 degrees. So it's a torus which enjoys the Z6 symmetry. And let's consider D2 brane wrapped on this torus. And this will be our initial BCFT that we understand very well, that is described just very wise free bosons. So there is one combination of the cosines of those fields, which has this conformal dimension. It goes like 1 over r squared, this coefficient, due to the 120 degree. And the OPE of that operator, or like, is like the fusion rule, to say, is like that it goes to 1 plus itself. Okay. And for r greater than 2 over square root of c, you can see that this h is less than 1. So this is a relevant operator or tachyon, so we expect a condensation. And since everything are free fields, then we can calculate the structure constants. We can plug it to string field theory and see what happens. And we find this surprising, so this is the torus, and this is the plot of the energy density. I didn't tell you what energy density here is. So we are considering time-independent solutions, so therefore the width and action is equal to minus the energy. So is the total energy. But this is energy density, so this is something that we extract from the boundary state, and the boundary state is given by combinations of Ishibashi states based on the primaries of the bulk theory. They are given by harmonics of like exponentials of the free boson with some integer coefficients.
Can you define energy in the language of CFT?
CFT?
Yes.
Well, this is a
energy density, I mean.
Yes, we can.
You can.
Yeah, we can. It's some component of the boundary state. Yeah, you extract it from the boundary state.
What prevents the usual open string tachyon from condensing?
The good question. So this is not prevented, of course, but this is the potential depends on many fields, like essentially infinitely many fields. So if you truncate it to some level, you have like 2 to 100,000 solutions. And you can kind of see when things are under control, and they are not always under control, but in this case they are under control, you can kind of see which tachyon condenses dominantly. And so there are solutions when only the universal tachyon condenses, and these are the old solutions from '98. But in this case, what condenses dominantly are these tachyons corresponding to this vertex operator. And the universal tachyon also gets some expectation value, but much smaller. Okay, and
The idea is that this will be an exact solution.
Oh, it is, yes, it is.
So that then the other tachyon would condense, but that's another issue.
Oh yeah, so this solution itself is unstable. So there is like this tachyon still living on this configuration. Yeah. And so we see that the solution is kind of weird because, well, we know there are some other solutions where we find like D-branes, so they correspond like to quite localized lines along the torus, or D0-branes, which where the energy density is concentrated at some points. But this is kind of smeared. This is like really weird. And so we were puzzled about this for a long time. And then actually my student Voshmera discovered that this has already been found in 1997 by Yi and Kane in a condensed matter paper. I can't tell you about the physics, but it concerns multi-channel Luttinger liquids. And that the G function is some mobility in that system. And okay, I won't tell you much about the condensed matter interpretation. So unfortunately, we didn't find anything new, except that we can calculate the G function much more precisely than they were able to. These are some raw string field theory data from numerical solutions up to level 12. So we start from level 2 and we go to level 12, then we can do fits to infinity. And the fit is this black line, which goes around, start this value 2, and here goes to here goes to 1. And actually the solution, so this is a plot, actually each of these points is like that solution that we follow for different value of the radius. So the solution starts at this radius 2 over square root of 3, and the value is given by essentially in these units by volume of the D2 brane, which is essentially the volume of the equilateral whatever the square, the tilted square, or how do you say it? Sorry? Parallelogram. Yeah, parallelogram. Yeah. And so it's a solution essentially which interpolates between this D2 brane, and here at this radius square root of 3, it interpolates to 2 D0 branes, but it's different from that. So here we plot parabola, which gives you exactly the tension of the D2 brane, because it squares as the volume, squares of the area. So it's a parabola. So the G function of the black line is like clearly smaller than the blue line, even though it's very close here. And yeah, so this is something. This is how it looks like. So actually, there is this there is this special point, square root of 2, where the solution can be constructed explicitly by conformal embedding of the C equal to 3 boson into this Gepner-like thing. Is given by product of 3 minimal models, Ising, critical Ising and Potts with these central charges. So you can check this identity. And well, you can work out that there is this correspondence between the cylinder partition functions that was worked out by Affle, Koshikawa, Seller, and we can calculate the coefficients of the boundary state analytically, and they agree with this numerical values as well. So so analogous conformal embedding techniques were used by Jakub in this paper, where we looked at the superstring at T4, and we found stable half VPS, quarter VPS, but also some stable non-VPS states, which are not of the usual form.
So at this point, does it become sharp lines, or is it still fuzzy if you draw the energies of the resulting configuration? I mean, there you can give an analytic function of the boundary state, right? For the Ising, tricritical Ising and Potts model. So can you then translate it back into an energy density and plot it and compare this hexagonal shape that you showed?
Yeah, sure.
But is it then a sharp line?
No, okay. That's a good question. I don't know. I haven't looked at the shape at this particular radius. Maybe it accidentally becomes sharp if there is a good reason for it, but I don't see a reason why it should become sharp.
It's a very special rational type construction, so you would expect something sort of more
beautiful. Maybe.
Let's say simple.
I think you are maybe a bit optimistic, but we will check. Yes, that's a good suggestion. Yeah. So, so we can use this level truncated numerical open string field theory to calculate the G function dependence on the radius with several digit accuracy, and this is a numerical fit to our raw data. So R0 is this critical radius where it becomes, okay? And then what I will describe in the second third of this talk, we can calculate using an exact analytic solution these numbers analytically, and at least you recognize these numbers. And they actually, this number is with 10 to minus 5 accuracy. This is 10 to minus 4 accuracy. So we have the string field theory calculations under very reasonable control. Of course, you could go to higher, but okay. So now let me describe these analytic considerations that are based on this work with Jaroslav Scheinflug that appeared in January last year. So we are interested in constructing classical solutions that correspond to deformations by weakly relevant operators. Okay, so it's known from the work of Affleck and Ludwig in 1991 that the G function changes under such a RG flow in this way, where Y is the departure from exact marginality. So it's important that the 3-point function should be non-zero for this to work. Actually, in this original paper, they quoted this result on one line without justifying it, but then it turned out to be quite a difficult calculation. Takes typically 2 pages in a PhD thesis, and no one dared to go to higher order. But actually, I can show you that this formula can be derived on one line using sense conjectures, and that the calculation to next to leading order is quite feasible. So the open string field theory equations of motion, when we gauge fix them, they took this form. We split the string field into the relevant part, I mean relevant in the sense that we are interested in it in this form, and some rest that we are not so interested. We split the equation into 2 forms, introducing these 2 projectors, P and P bar. And then we can solve this second equation. So it looks like a quadratic equation for X. So if everything were just normal numbers, we would just use the formula for quadratic equation. And actually, you would get, and if you would Taylor expand it, you would get Catalan numbers in the expansion of the square root formula, okay? And they actually count the number of planar binary trees, and these are like the Feynman diagrams that we get here. So essentially, everything that could appear appears here, described by these planar binary trees. So essentially, so the H plays a role of a propagator. Then we have R squared, the Witten vertex. And then we can use all sorts of bracketings. So the number of bracketings is also given by Catalan numbers. So everything is under very simple control. We can, yeah, it takes no work to write this to arbitrary high order. And it's a fun exercise to show that the unfixed gauge equations of motion, like this Q here and without the B naught here, they are a consequence of this explicit solution. But also if this condition is satisfied, okay, so then one can show the full equations are satisfied. Okay, so now I show you the leading order calculation. So this is the equation for R. The P projects this R star R. So it's some string field that P projects to the respective component and proportional to CV. And this equation is essentially analogous to condition that the beta function of the coupling lambda of given by the perturbing operator is 0. Okay, so to solve that equation, I mean, it's simple because the star product gives you this C structure constants, and this Q gives you the Y, and so you read off immediately that R is equal to this multiple of CV. And now that the one-line derivation of Affleck-Oshikawa result is that you get delta G is 2 pi squared times S. This is SAN, and then you have 1/2 minus 1/2 plus 1/3 from Witten, and then you plug this in and you get this result. Okay, so to go to the next leading order, I have to hurry a little bit up. So it's very straightforward. There are no singularities, but there are some technical obstacles. So we have to calculate this 4-point function with these kind of exponentials of Virasoro operators. This is also essentially integral of e to minus TL naught. So this looks like a normal ordering problem or mathematically Bruja decomposition in the context of Virasoro group. But there are some tricks that work, like inserting this Hodge decomposition, or or like using large stub vertices. These are some technical things that I don't have time to talk about, or flat non-cyclic vertices as of like 2 weeks ago that appeared in this paper. And the result is very simple, this formula, and it has no traces of string field theory. I mean, BC goes has evaporated, 3 times square root of 3 over 4 has evaporated, and we are left with this very simple formula, which is free of any ultraviolet or IR ambiguities. Yeah, this is because this is value for G. This is value for G, and G is a physical quantity, so it's not scheme dependent. G is not. Yeah, the beta function is dependent, the coupling is dependent, but G is not dependent. Okay, so in the last third of the talk, which I have, I think, like 2-3 minutes. So let's see what can we do in closed string field theory. So this was addressed by Sen and Mukherjee, 1991. But there is an immediate problem that under the RG flow, the central charge typically decreases. So this would violate the criticality of the matter CFT. Okay, so what they proposed, and recently was also used by this group at Harvard, they took a CFT with some central charge C and then accompanied it by a linear dilaton with some background charge, and they took the central charge, so to compensate the original central charge, so the total matter central charge is 26. And they showed that due to the Gauss dilaton, after the condensation, the C total, so the central charge of the linear dilaton readjusts, so that the total central charge is 0. So everything looks nice. But I personally am not so happy about using linear dilaton. Maybe it would be better to use Liouville theory. And the things are under progress. But one could also try to use like something like purely like minimal models. But if you want to have something parametrically weakly relevant, then typically the central charges of such theories are some integer minus some positive epsilon. So like for minimal models, you have like they at large p, they go to like 1 minus something like that goes like p6 over p squared. And you would have to compensate it by something like that, and this doesn't look quite right in the context of unitary CFTs. But for example, we can take the Baldacci-Auguri ADS3 background of non-unitary SL2R, the Simeon-Witten model, and then it actually has this property. So this is how we could compensate it instead of the linear dilaton, which I think would be very nice. So what we have found is that, well, we solved analogously, perturbatively, these equations of motion coming from the closed string field theory equations of motion. Again, we split into 2 parts, and we do some little calculation. So we recovered the result, or we use the result of Ludwig and Cardy, and what we find is that the closed string field theory action changes, the value is like minus 1/12 of the change of the central charge. So we use this formula by Ludwig and Cardy as an input. Surprisingly, we find that this persists where we go to next to leading order. There was a like impressive calculation by Dan Jaroslav, and this is a very concrete finite formula. And we check this for large unitary minimal models, and it agrees with some relatively recent calculation by Pogosyan and Pogosyan. So as was pointed out recently by Shi and company, and also Ashok in the old days, so at third order there is this obstruction due to the Gauss dilaton. So the dilaton gets expectation value, and things get bad. So they are not so much under control. And that's the reason why they use the linear dilaton, where things, where essentially the ghost dilaton can be ignored. But so let me just conclude. So including the ghost dilaton, it's still possible to show that the closed string field action on a classical solution is equal to 0, as argued by Erler using arguments of Bergman and Zwiebach. But it's rather mysterious. I would say that if we ignore the ghost dilaton, we get a shift that is given by 1/12 of the change of the central charge, even to next to leading order. In principle, you would expect, if you do something wrong, you would expect complete mass and not something nice to persist to higher order. Of course, there is this question, what is the physics of the endpoint theory with the lower C? So, yeah. And so one idea that I had, which we are still thinking about, is that maybe for consistency of string field theory, we should always, even in the critical case, we should tensor it with some C equals 0 Liouville background, and so that there is something that can adjust. Of course, it's a non-unitary theory, but and I think as a final remark, I think there are some interesting lessons for a general structure of conformal perturbation theory that remain to be elaborated. Okay, thank you.
This is not quite a question so much as two comments. Is that acceptable? Okay, yeah, it's like one of the comments is that about the basically the equation here, we're basically doing it by ignoring the ghost dilaton. We do exhibit an example of this exact calculation, but only as for leading order, where you actually do keep track of the dilaton, you keep track of the correction to the linear dilaton thing. You're using the absorber center charge, and everything does indeed work out. The other comment is that it seems to be possible, we're still trying to work this out, it seems to be possible that you can actually just directly just like write down a string field theory action that's consistent, where the worldsheet CFT just has a wrong central charge. And in this case, if you have like a linear term to the action, so 0 field is not a solution. But it seems like you just write, I already have written down like just the explicit, like the first order correction to the action, and I'm still like, it's a bit of a combinatorial mess for like the higher orders, but like it seems to be there's not really an obstruction to doing this.
Oh, that's an interesting proposal. Yeah. And I was reading your paper on the airplane coming here, so it just came out. Yeah.
So it is about the scheme dependence. So I think, yeah, it is true that the G function is not scheme dependent, but Y is scheme dependent, right?
Why?
Yeah, the perturbation parameter.
Why would you say so? It's a difference of, it's a departure of the conformal weight from identity.
It's 1 minus h.
It's 1 minus h.
That's at the origin, right? But once you go far away, I mean, is it clear that Y still has that interpretation?
It's just a number, it's 1 minus h.
Yeah, I mean, I'm just saying, is it still the 1 minus h? And that's not completely clear, right? I mean, because Y is, in your case, is the expectation value of the string
You
field,
mean
right?
if we deform the theory a little bit, then the conformal dimension of the operator itself changes?
Yeah.
Yeah.
I don't know. I mean,
Yeah, that's right. That's why we need to consider family of CFTs with.
I mean, you could probably calculate the conformal dimension of this operator at the minimum, right? Which will be irrelevant, and that could give another data which one could compare with what you have.
I see.
It's not supposed to represent the amount, the size of the deformation. It's just some small number that you be able to use to control the perturbation.
I see. So you are saying it's not scheme dependent. It's just the value at the original maximum. Okay.
Can you also use string field theory to compute the BCFT data?
Yeah, we can calculate all the coefficients of the boundary state. And there are some tools to calculate the weights of the operators in the new BCFT. But those are a bit more complicated. Well, Ashok has some recipe to calculate that. And then the next step is to calculate the 3-point structure constants for the boundary operators. But to my knowledge, no one has really done that. It's a really complicated calculation. But the boundary state coefficients are, I mean, we can calculate.
Just maybe one comment about terminology. When you said multi-component Latinger liquid,
Yeah.
I mean, this is the same as two compact bosons. It's just exactly the same thing.
Really?
So it's not like a different, I think, yeah. I mean, it's just equal.
Okay, thank you.
Have you estimated the decay rate of the D2 brane to the condensation of tachyons?
No. No, not me, yeah, but yeah, there have been works on this topic by, I think, by Juan and Andy, like in the early 2000s. Maybe Juan would comment on this.
It's really off shell, right? You're looking at the field configuration space and asking about some flow through the field space, through the string field space, from one extremum to another. It's not a dynamical process, right? You're just looking at RG flows.
But then we expect the D-branes have some lifetime, no? Then we could ask what's their lifetime.
Well, back in the day, there were sort of two complementary points of view. One was you just look at some off-shell configuration space that you're making some trajectory through.
Yeah.
And the other was to think about it as a dynamical process.
Yeah, right.
In time-dependent solutions. And you're just looking at two different processes.
Okay.
Other questions? All right, let's thank Martin.